to talk a little bit about QCD, quantum chromodynamics. What in the world is that? Quantum chromodynamics. It's got to do with color, chromo, right? And I'm going to begin more or less where I left off the other day. And it's got to do with these two individuals. They're considered the best mathematicians on the planet, or among the best. One is Witten, the other one is Susskind. And what I said the other day is these people are working on nonsense, on poppycock, on stuff that doesn't exist. So even if they are the best mathematicians on the planet, right, they're developing equations for stuff that doesn't exist. They might as well, just throw your tax money away, which is what they're doing, okay? So here they are. These are the two fellows I'm referring to, okay, for those of you who know them. They develop equations for what? For nonsense called black hole, for dark matter, and for rubber bands. All right, this is what they develop equations for, and and this is what you're spending your money on when you give them money, to Stanford University and the Princeton Advanced Studies and so on. This is what they spend their money on, and they're not the only two. Lots of these mathematicians are developing equations for inexistent spirits. That's what they're doing. So even if they are the best mathematicians in the world, it wouldn't matter a bit. Their entire work is worthless. It's meaningless, okay? And these are other things that they're working on, like we talked about the other day, the holographic universe, wormholes. That's what they do. They develop equations for inexistent poppycock, nonsense, stuff that doesn't exist. What are these people looking for? They're looking for gravity, and they can't find it. And all they had to do all these years is abandon math, because math is not going to tell them what's out there, how Mother Nature and Father Universe run their shops, right? What's going to do it is they have to do some armchair physics, lay back, forget about math, try to visualize, how gravity works. And for that, you need objects, you need things. And one of the things that you'll notice in mathematical physics is that they don't have things. They don't have objects. They don't have entities, bodies. What they have is mathematical concepts that they have reified, they converted, they concretized them, they turned them into physical objects, and they move them around as if they were objects. And that's where the problem is. The problem is they don't have, in all of mathematical physics, you will not find objects, things. And that was the whole, mystery. If you can't do physics without an object. And they never learned that basic, law or principle. And so as far as I'm concerned, these people could be developing equations for dark unicorns and black leprechauns because their work is totally in vain. It's worthless. It's they're wasting their time, your money. That's it. Okay, that's in a nutshell. But these people work primarily on, stuff that's out there in the universe, the big world, the world of big, macro world. And it's like Gulliver here, Gulliver, he was in Brobdingnag, and he dealt with a macro world, right? But you also have to deal with a micro world of Lilliputians, right? And so that's the world of quantum mechanics. And that's a little bit of what we're going to talk about today, because the subject matter is QCD, quantum chromodynamics, quantum meaning the atomic and subatomic world. Okay, how does that work? Okay, now there were a couple questions that were asked. The first one at the beginning of the 19th century was, why didn't the electron fall all the way to the nucleus, right? I mean, here you have the negative ball, right? Why does it circle around, or why is it always around the nucleus? Why doesn't it fall all the way to the nucleus? What prevents it from circling, losing energy, whatever that is, right? And slowly, falling into the nucleus. And that was a question that they were trying to answer. They never answered it to this day. All we have is some nonsense about orbitals, about energy levels, and they say the electron cannot go beyond that energy level. which is a mathematical description and saying it is so, but they never explain why it is so. What physically restrains the electron, right, from going beyond the energy levels? That's one issue. They never answer that question. Another question came up after 1919 when Ernst Rutherford allegedly discovered a proton. And since the electron was negative, the proton had to be positive, so we had a positive bowling ball, and a negative bead going around it. Negative bead had a lot less mass, right? But the point here was that you had these two different charges, the positive charge and the negative charge. But if all atoms were made of protons in the center, and the nucleus of all atoms were made out of protons, why didn't all these positive charges repel each other, and why didn't the nucleus blow apart? Why didn't it explode? You got all these protons, these positive protons. And so one of the questions that came up in the 1920s was, why does the nucleus stay, more or less as a ball? Why doesn't it explode with all these protons, just repelling each other? And so that's the question that I'm going to try to answer today. In other words, that's what the whole lecture is about, trying to answer that question. Okay, see if we can answer it. See if we have an answer today, not from rationality, but from quantum mechanics. I mean, do they have an answer? Do the quantum mechanics have answers to that question? Okay, in order to understand a little bit of how this works, or how they got to these answers, right, we need to start at the beginning. And I started the other day, I'm just going to go briefly through it, that they had to invent quarks, okay, 3 quarks, okay, 3 quarks for Muster Mark, okay, or whatever. And it's more or less like this, very quickly. They talk about charge, so I put charge cards there. I think anybody understands that. And we have 2 visas and a MasterCard for the proton. What do I mean by that? Well, if you have $66 in your visa, in each one of your visa cards, and you have a negative 33, because that's what the MasterCard is, a negative number, a negative value, negative charge, negative 33, well, you can understand mathematically how you can add the 2 visas, 66 plus 66, you end up with around 133. You subtract the 33 from the MasterCard, and you have a net of 1, right? And that's the charge on the proton, which is 1.6 times 10 to the minus 19 coulombs, right? How about the neutron? It has no charge. How do we get to there with this same scheme? Well, here it's the other way around. You have 2 down quarks, meaning 2 MasterCards, 1 up quark, which is the visa there, right? And so what is a down quark? Well, it's a negative 1/3, okay? So we just putting numbers there to make it easy. You get 2 charge cards. Each one has negative $33, right? So you get a total of negative 66. But you have in your visa, you have a positive 66, which is the value of the visa, right? Of the up quark. And if you do the math, you get 0. And that explains why the neutron has no charge. So this was the scheme they invented to explain why proton has charge, neutron has no charge. Straightforward. They got a Nobel for this. That's incredible. But this was the scheme they invented. Okay. So we explain, quotations on that, why the proton has charge, why the neutron does not have charge. Okay, great. Okay, but in order to still answer the question of, here you have the protons, they all have charge, they all have positive charges. How is it that something, whatever, right, prevents them from repelling each other, all these positive charges, okay? And so we ended up with this. Here I show it. This is what we're trying to explain, right? Why do protons do not push each other away? Why don't they repel each other and blow apart? Now, you can see those green ones there. Those are the neutrons. And originally, one of the ideas that was thrown around when the scheme came out, right, or trying to answer that question, right, they came up with saying that the neutron served as an insulator. It isolated the positive proton charges. Okay, so it served as a mediator right between the protons, and they had different answers to that question. They said, well, no, that can't be. I can only give you my version. Okay, this is absolutely mine. It has nothing to do with really quantum, but you can see where I'm coming from with this argument. And that is that here you have deuterium, right? Deuterium is a hydrogen atom. It's a isotope of a hydrogen atom. It's got a neutron, which the hydrogen atom does not have, right? And so the question is, well, why does it have a neutron, deuterium, right? Because it's not separating any two protons there. So why did God, the devil, or Mother Nature, whoever, right, put a neutron in there? And tritium has two neutrons. So obviously the neutron's job, its purpose, was not to separate protons, because tritium and deuterium kind of overthrow that theory. Okay, so that's my take on that. But they had other reasons for rejecting that, and so they looked further and they tried to figure out why the protons don't repel each other. For this, you need to understand the notion of a value that they created called spin. Okay, you need to understand spin. And the first problem is that you will never understand it. You will never understand spin for two reasons. The last 100 years since they invented spin, no one has been able to define spin. Okay? Part of the problem is they use the word spin, and they all tell you the same thing. Listen, because you'll hear this, or you'll see this everywhere. They say spin is not spin. In other words, spin is not like a top. You spin a top, we all understand that. Or a skater, spinning, no problem. We all understand spin. And the first thing they tell you is spin is not spin. Spin for an electron, for any subatomic particle, is not like the spin of a skater or a top. Okay? Straightforward. Okay? And then the next thing they do is they show you, they illustrate it, and they tell you that spin is like a top. So we have these contradictions that the mathematicians live with, where on the one hand they say, well, it's just a number, spin is just a quantum number, and on the other they try to give it a physical interpretation. They can't. They deny that spin is spin, like a top, and then the first thing they do is use spin like a top to give you their physical interpretation. And it's like they get away with murder. They have all these contradictions, they just live with them. And so, no, you will never understand spin because it's never been defined. Here's the Wikipedia version of spin, okay, synthesized for you. I just pulled out the important parts, right? As the name suggests, spin was originally conceived as a rotation of a particle around some axis, right? Historically, orbital angular momentum related to particle orbits. While the names based on mechanical models have survived, the physical explanation has not. In other words, it's not spin. It's not like a top spin, okay? It says quantization fundamentally alters the character of both spin and orbital angular momentum. Since elementary particles are point-like, self-rotation is not well defined for them. Wrong statement. They always have these wishy-washy statements. Now, if it's point-like, it does not. It's not. You can't say it's not well defined. It does not have. That's the correct way of stating that. But see, they always have this wishy-washy language. They say, it's not well defined. No, it doesn't exist. If it's a point like it, they can't rotate, period. Okay, that's the way you should state it. Straightforward. Anyways, the point here is that spin is not spin. That's what they're telling you in your face. They don't tell you what it is. They tell you what it ain't. And what it ain't is top spinning. Okay, we'll call it top spin. Okay. Here's the AI, okay, the robot. See, if we ask him, he might know, what spin is. It says quantum spin versus classical spin. Classical meaning rational spin, right? Like a top spins. In classical physics, a spinning object like a top has a clearly defined axis of rotation and a predictable orientation. Quantum spin, on the other hand, is an intrinsic property of particles, whatever that means, right? That doesn't require a physical axis of rotation. In other words, they're telling you what it ain't. They haven't told you yet what it is, okay? Quantum mechanics introduces the idea of particles existing in multiple states at once. In other words, irrationality. They're saying that a particle can have different states. It can be everywhere, it can be at a single place, it can have superpositions, it can have all these different states, and they get away with murder because this is just Alice in Wonderland magic. They're saying they can have all these multiple states. It says, and their spin orientations are not fixed but probabilistic. In other words, it's a probability, whatever that is, right? It's again, they're taking it into math world. It's got nothing to do with a physical world. They can't make sense of this in the physical terms. This is different from the deterministic nature of a spinning top's orientation, meaning it's not a top. It's not like a top, okay? And then spin is a form of angular momentum, whatever that is, a form of it. What do you mean? What kind of form? What type of angular momentum is it? But it's different from the orbital angular momentum of a particle moving around another particle, right? Spinning is an inherent property of the particle itself. So they say all this nonsense, they never tell you what spin is. They just tell you what it ain't, and they say, well, it's some kind of angular momentum. You try to figure out what we're talking about. Oh, okay. I'll see what I can do. And here's another, just in case, one more. Okay, this is from a couple sources, but I synthesize them here. It says, physicists have not yet developed a visualization of physical reality that underlies spin. In other words, they cannot tell you what spin is after 100 years, right? Since we've known spin. The dynamics of spin minus half objects cannot be accurately described using classical physics. No kidding. I mean, what do you mean minus half? What kind of spin is that? What is this nonsense of minus half? How can you put a number to the spin of a top, for example, right? They require quantum mechanics to describe them, no doubt. Quantum mechanics is irrational explanations. That's what they mean by quantum mechanics. That's why they need quantum mechanics to describe them. As such, the study of the behavior of spin minus half systems forms a central part of quantum mechanics. The key to understanding spin is to what? Realize that whatever it really is, what it really is, right? Its physical manifestation is magnetism. Well, it turns out that, they're going to talk later on about spin, and they are not going to relate it to magnetism, especially when you get to this color charge. It's got nothing to do with electromagnetism. But see, they have all these contradictions, and they just live with them, okay? So it says, what the theorists are predicting, they always predict, right, is the magnetic properties of quantum particles, not their rotational motion. So they're going to be talking about spin. They're going to be referring to magnetic properties and not to rotational motion. Okay? The axis of spin of an electron can point any which way, and the electron spins around it. What do you mean spins around it? Well, what are you saying there? I mean, you just told me that spin is not spin. Now you're saying the electron spins. It could spin clockwise or counterclockwise around the arrow. Well, again, so they deny what they just finished saying. On the one hand, they said you cannot imagine spin because it's not the classical spin, meaning rational spin, what the word spin really means, you spinning of a top. And then they immediately say, well, you got this arrow in it and the electron is spinning around it, which is the description of spin. And so, yeah, you'll never know what spin is, right? You'll never figure it out. And so, yeah, and you find these notions when they talk about not only numbers, but they talk about upspin and downspin. What is a spin up, spin down? Whoa. I mean, does the top go up and down? Does it jump up and down? Does it rotate in the north-south direction? I mean, what are they talking about when they say spin up, spin down? Okay, again, what kind of tops do these quantum people play with? That's the question. Okay, so on the one hand, they deny that spin is spin, like a top. And then the next thing they do, they illustrate it as a spinning top. Okay? So, you see the top spinning on the left, and the one on the right is from different websites. Essentially, they all say the same thing, and they show you the electron spinning clockwise or counterclockwise. That's what they're showing you. Okay? So spin is spin, but it ain't spin. And they just live with these contradictions, and they get away with them, right? And here you have one fellow. His name is James Lincoln. He's from UCLA, and he's going to explain to you exactly what spin is, okay? So If you had doubts, well, listen to a teacher, to a professor, right? I mean, they should know. Listen to him. Here goes.
It was discovered that electrons had a property called spin. That is, the electron was spinning as it circled the nucleus. It's the alignment of these electrons' spins that results in the magnetic properties of iron.
Okay, so now you know what spin is. Spin is this, which is spin, right? So they, on the one hand, they go out of their way to deny that spin is spin, like a top spins, and then on the other hand, they illustrate it and they talk about spin as if it were a top spinning. And they've just been doing this for 100 years, and they never define spin. They just tell you what it ain't, and it ain't like a top spins. So you figured it out. Okay, what's the problem with spin as it relates to quarks inside? You know, remember, you need 3 quarks to make a proton. You need 3 quarks to make a neutron. 2 up quarks, 1 down quarks for the proton, 2 down quarks, 1 up quark for the neutron, right? So the question is why? How does spin enter the picture here? Well, it enters because, see, the quarks can only have one of 2 types of spins. You can have a positive half or a negative half spin, whatever that means. Okay, forget about what it means in physical terms. Don't try to visualize it. These are just numbers, quantum numbers. So these guys can have positive spin or negative half spin. Positive half, negative half, right? But if you have 3 quarks inside inside a proton, inside a neutron, well, 2 of them will have the same spin state. 2 of them will have positive, or 2 of them will have negative half spin. And you can't have that because the Pauli exclusion principle says that no 2 particles can have the same quantum number, the same state. Okay, so we have a problem there because here we have, let me show you, we'll have these 3 quarks, and 2 of them will have the same spin no matter how you twist the thing. Okay, so here's the problem. Okay, if there are 3 quarks in protons, 2 quarks would have the same spin. That's the issue. This violates the well-established Pauli exclusion principle of quantum mechanics that says that 2 particles cannot have the same quantum state. Okay, ergo, the mathematicians came up with a scheme. They invented a new type of charge called color charge. Okay, so they created this out of the thin air. They took their magic wand, okay, and they said, okay, we're going to create a new type of charge that we cannot measure, right? Because they can't measure these things because it's inside the proton. They can't dig in there to find. They just try to figure it out mathematically after smashing protons that, oh, this is probably what's happening in there. And they have all these theories, right? But they had to create this thing called color charge. Why color? Color because you have the 3 primary colors there, I guess, red, green, and blue. And with those, you can create mixtures of them, among them white. White being, if you mix all 3, you get white. White means it has no color, colorless, however you want to interpret that. 0, okay, 0 charge or 0 color charge, right? Okay, so they invented this color charge, and that way they could get away with putting the 3 quarks inside the proton, inside the neutron, because now they don't all have the same state, the same quantum numbers. So they created a new quantum numbers in order to make this scheme work, okay? And they called it quantum chromodynamics, okay? So there you see it. Even though, 2 of these up quarks have plus half, or the green and the blue one have minus half, it doesn't matter. Because even though those numbers match, what does not match is the color. The color is different now, okay, between all 3 of them. And they always have to have different color, the quarks. One is red, one is green, one is blue, okay? And that's called chromodynamics. Now you know why, because it's got to do with colors, okay? And again, it's got to do not with color per se, it's just the scheme is the same as the world of colors, okay? That's all they're saying. And here we have one of the great mathematicians out there who's on the internet, and he's going to explain it to you so that you understand it perfectly well, so that you don't say that I came up with all this nonsense, okay? So here's Arvin Ash, and he's going to tell it to you in his own words. Listen carefully.
One of the detected particles, called a delta particle, was composed of 3 of the same quarks, up, and up, for example. In that case, since these particles all have a spin of 1/2, we can have one particle that is spin plus 1/2, one that is minus 1/2, but the third one would have to have either a positive 1/2 spin or negative 1/2 spin, making it identical to one of the other up quarks. This would violate the Pauli exclusion principle. So how is it that a delta particle can exist with 3 of the same types of quarks? This additional property is now called color. This has nothing to do with the color that you can see with your eyes. It's a metaphor for a kind of charge, a color charge. So if this was the case, the 3 similar up quarks would not be identical because they would have different color charges, and thus they would not violate the Pauli exclusion principle.
So what was the purpose of inventing this color charge? Was just to accommodate 3 quarks in there without violating the well-established Pauli exclusion principle. That was it. So it was a scheme that they invented. They invented first the quarks, then they invented this color charge so that they could avoid, the Pauli exclusion principle. It's all math. It's got nothing to do with physics. It's all math, just math. And so they explain it in mathematical terms, not in physical terms. They cannot explain it in physical terms, partly because they don't have definitions. They don't know what color charge is. They don't know what spin is. They don't know what a quark is. They don't know what any of these things are. And so it's just a mathematical scheme. That's all it is. And they get Nobel Prizes for coming up with this poppycock. Okay? Then they get more equations trying to figure out, they can describe even further in more detail the same nonsense. Okay, they've never seen a quark, they've never seen a gluon, they don't know what we're talking about. They're just developing equations based on their notion of what they think is in there. Okay, so here it's important to note just one thing. Here it's quarks were blessed with fractions of electromagnetic charge and spin, and now have an additional property known as color charge. Each quark inside a proton or neutron has a different color, red, green, or blue. Blend the 3 together and you have what? White. No color charge. This explains why protons and neutrons don't have color charge. Or you can say they live with a colorless, singlet state. In other words, you can say they're colorless, or any way you want to put it. These are just words. All they're saying is it's not like the quarks, which do have color, or like the gluons. The protons and the neutrons, overall, they don't have a color charge. They're white, 0 color charge. And that's why I guess they can't measure the color charge on a proton because it has none. Okay, it's inside the proton, the little ball there, the sphere. Okay. And here you have the quarks throwing gluon balls at each other. This is how it's illustrated. And these gluon balls are the ones that change the color. They carry the strong force, and you can see that they're colored also. The gluons have colors, and by jumping to the other quark, they change the color of the quark, but at all times they have to have 3 different colors. And one thing that is very misleading about this picture, which they always show out there, that people are not aware of, is that there are gazillions of quarks and gluons inside a proton, inside a neutron. These are just what you could call the valence quarks, but there are gazillions of virtual quarks, virtual gluons, gazillions of them, coming into existence and annihilating each other constantly. So net, there's always 3, right? That really is what they need for their mathematics. But then they've got all these other things going on in there, a lot of activity inside a proton, right? With all these little particles coming into and out of existence. They're all virtual particles, meaning magical particles. They come into being at the end of a magic wand. You go blah, 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 right? Abracadabra. And so what does it mean to annihilate? What do they mean when the particle annihilates itself? See, coming into existence, they come into existence from where? From space? I don't know. Maybe they are space particles. Space is made out of particles, and so suddenly one of these leaves space and comes into the real world very temporarily, like a split gazillions of a second, and goes back to being part of space. So they come into being and out of being, right? And then when they annihilate themselves, what does that mean? Do they turn into space again? Well, not in mathematics, because in mathematics, quantum mathematics, you don't turn into space, because space is considered to be something in the religion of mathematics, okay? And so what it does is turns into energy. And what is energy? A concept, mathematical concept, okay? So when they say annihilation, they're saying that particles, two balls, turn into energy, whatever energy is, some puff of smoke maybe, right? And since all of space is filled with this energy thingy, when energy wants to come back into the real world, it comes back as to virtual particles. And so this is just a bunch of hocus pocus that they've created to explain what they cannot explain. It's just magic to the 100th degree. I mean, it's just magic. It's just Alice in Wonderland magic. That's all it is. Virtual particles is absolute nonsense. If they have to introduce particles which they create as needed by the mathematician, that's not physics. That's just garbage. Poppycock. Okay? That's what we call it in physics. Okay, so here you have these little gluon particles going from quark to quark. They change the colors. Great. Okay? And so let's draw some conclusions from all this. So far, we still haven't begun the class, really. This is just the introduction. Conclusions. Quantum mathematicians invented quarks to what? Explain why protons have electromagnetic charge and neutrons don't. Okay, that was the reason for quarks. Okay, that's how Gell-Mann and Feynman and all these people, it was Vicky, they invented all this nonsense just to try to come up with a scheme to explain what's going on in that invisible world. Okay, and of course, when they predict, they always prove their predictions, always, because otherwise they don't get a Nobel, and otherwise they have to start over, come up with a different scheme. That scheme was good enough for the mathematician. They said, let's run with it. And that's how they prove theories in the religion of mathematics. There are these quarks inside protons and neutrons, plus gazillions of virtual quarks and gluons that constantly pop into and out of existence inside the unidentified, because they never identify that, the fermionic sphere. They always put a sphere around the three quarks. And you say, what is that sphere? What is that ball? And they never define it. They say, well, that whole thing, that's the proton, that's the neutron. It's a fermion, whatever that is, right? So they put these balls encapsulating three quarks, and that ball is there, put in by hand. They never define what that is, okay? And of course, if you have the quarks bound by, these gluon springs, and then you also have this prison around them, this, enclosure, well, you can understand why the quarks don't leave the fermionic ball, because they're bound by the gluons inwards, and they can't leave even if they wanted to, because they have this shell, this membrane that, constrains them. Okay, quarks can only have plus half and minus half spins. This creates a problem, partly because spin has never been defined, never will be. Okay, they can't define it, they never will define spin. Okay, otherwise, the day they define it, they lose. Their whole religion goes down the drain. So they can't define spin because it would destroy quantum mechanics. Therefore, a third quark would also necessarily have either a plus or a negative half spin, right? And violate Pauli's exclusion principle, because it says no two particles can have the same quantum state, whatever that is. State of Maine, Maryland, I don't know what state. So the quantum mathematicians invented a new kind of charge known as color charge, okay? Quantum chromodynamics, to skirt the Pauli exclusion principle. That was the reason they created all this nonsense. This is the foundation of modern quantum mechanics, even though quantum mechanics is dead already. It's dead because they created quantum field theory, QFT, and field is the opposite of quantum. Quantum is a ball, a discrete bundle of whatever, of energy they call it. And field is exactly the opposite. Field is energy that is spread out all the way to the end of space-time. Okay? So what they did was they merged the discrete with the elongated, with the extended. And that's what quantum field theory is. That's why it's so successful, because when they introduced the field, they got rid of the quantum. Okay? That's what they destroyed, the notion of quantum that they had at the beginning of the 20th century, which was the discrete ball, or the discrete number, the discrete bundle of energy. That's gone. Okay, they can't use that anymore because they cannot merge that with general relativity, meaning they cannot explain gravity, the unification of forces, right? Theory of everything. That's where the problem is.